Okay, so yesterday we did these examples, and we talked about how the expected value is something that can tell me what I can expect to make off of the individual, in the insurance company situations or the gambling situations. The expected value is what I can assume to make or lose off the individual if I am doing this on the population, doing essentially this trial, this technique an infinite number of times, this experiment an infinite number of times. So in that case that we did, one particular person might have a $20,000 loss, and the insurance company has to pay for that. But if we have 65 other people that are in this same insurance policy or have the same insurance policy and they don't have a claim, then those 65 people paying $300 a year are going to negate the loss that the company has of $20,000. Does that make sense? Or I guess it'd be $19,700. But over the long run, then, more and more and more people having the same policy, the insurance company can estimate or expect, I guess is a better word to say, that they're going to make, on average, $259.4 off of each policy that they insure having this $20,000 claim requirement. Does that make sense? Okay, so that's what we talked about yesterday. Now, when we talk about things that have means, okay, and we talk about these distributions, we can talk then about standard deviation as well. Okay, how far does a particular value fall from the mean? Okay, so probability distributions like data, okay, have standard deviations. Okay, so to calculate the standard deviation, sigma, okay, that's what that symbol, that lowercase letter sigma, if you remember back to chapter 2, and that, remember, we use the Greek letters when we're talking about parameters. Okay, so this is a numerical quantity that is representative of the population. So it says the standard deviation of a probability distribution, you first find each deviation from the expected value. Okay, so if in my formula, the deviations are the difference. Okay, how far are we away from the mean? Okay, then we square the deviations, and then we're going to multiply that deviation by its accompanying probability. Once we have that, we will then take all those individual deviations squared times their probabilities, and we're going to sum them together. That's what the sigma here stands for. Once you have that sum, you take the square root to find the standard deviation. Okay. So that being said, sometimes you're going to see this formula written differently. You guys remember what that variable represents? If sigma is standard deviation, what is sigma squared? Start with a V. That's your variance. Okay. So variance, a lot of times this definition or definition formula is defined differently. So they might say standard deviation and variance obviously are related. So they're going to say the sum of x minus mu squared p of x. They'll give you that. And then they will say, they'll put like a comma or a semicolon, and they'll say sigma then is equal to the square root of sigma squared, or standard deviation is equal to variance, the square root of the variance. Does that make sense to everybody? And they do that because this formula written underneath the root symbol can get kind of messy and challenging and daunting. And whenever we do standard deviation by hand, the variance is the first thing that you calculate. There's really no way of going around variance. Okay, so you're going to come in contact with that value first, and then it just makes sense then to take the square root. Okay, so you're going to see this formula a lot written this way. Okay, now we talked about standard deviation and variance back in chapter 2, and we went through the proof of standard deviation being able to be written in two different formulas. This formula is the formula, this is the one that I just wrote there, or just had there. That's the same thing, okay? But that requires me If I've got a variable that has like x is 0, x is 1, x is 2, x is 3, it takes on those three values. My discrete variable takes on those three values. Then I have to do, or four values, I have to do 4 deviations. I have to do 4 situations in which I subtract. Does that make sense? Okay. If I use this formula, how many times do I have to subtract? Because this says I'm going to sum a bunch of products, right? So there's no subtraction there in that summation. And that summation is where we're doing all these additional calculations, okay? I only have to subtract 1 time. Does that make sense? So yeah, I'm going to let you use whatever formula you want, okay? I think the way that I've predefined the next question in our notes is that we're going to use this one, okay? But we can as easily use this one, all right? Over the next couple days, when we have time, the examples that we do, we're going to do them in Excel, just so we don't have to do all the handwritten work, and we can set tables to do both these for us. Okay, we're going to see if they both equate to the same value. So let's get into an example then. All right, so if we have a fair set of dice, whether we do this with one die or 2 dice, it doesn't matter. But we're going to roll 2 dice. So I've got some fake dice here. If I roll them, okay. Well, yeah, but they're not. So we got a 5 and a 2, right? So 5 and a 2 on those. Okay. So this question here is saying let x, which is your discrete random variable, be the number of faces that show an even number, okay? So if I roll those 2 dice, how many of those faces show an even number? If I rolled a 5 and a 2? 1, okay? So my discrete variable can take on the value 1, right? Okay? If I roll them again, okay? So I got a 1 and a 3. How many faces there have an even number? None. So my discrete variable could take on a 0, right? And rolled and got 2 evens, okay? So how many faces can I have that are even numbers? 2. So my discrete variables, the 0, the 1, and the 2 here, are representing the number of faces that are going to land up with a even number on them, okay? Now, what I'm interested in is how often does that happen? If I'm rolling my dice, okay, we saw one situation where we got a 2 and a 5, okay, so that's 1 even, 1 odd, right? Here's a situation where we got an odd and an odd, okay, and I could keep rolling. How often does an odd and an odd show up? How often does an even and an even show up? How often does one and the other show up? Does that make sense? Does anybody know off the top of their head what that would look like? Not 7. So that's hard, right? That's a hard question to ask. So what we're looking at here is the need for a sample space. Would you agree that this would be a sample space of rolling 2 dice and identifying the numbers that show up on them? And then we can look at those and say, okay, if we look at, and there's patterns to this, so this isn't going to be extremely difficult to analyze, but would you agree that this one here is an odd and an odd? Okay, so that's no even faces, right? So this would be a situation. This is going to be part of the probability that is the discrete variable of 0. Okay, so there's an odd and an odd. Would you agree this is odd and odd? Would you agree that's odd and odd? So there's 3 in that column, right? Are there any odd and odds in this one? No, because this second row always has a 2 on it, right? What about odd and odd? Odd and odd, odd and odd, right? So there's 3 in that row or column. Any odd and odds in this one? Nope. What about this one? How many are in this one? 3 in this one. No odd and odds in this one, right? Okay, so what we find out, 3, 3, and 3, so we get 9 out of 36 that were both odd, okay? Now, that was, we could continue to look at the other discrete random variables with that table, but let's use some of our knowledge about probabilities. if I roll 2 dice, okay, and I can get no even numbers to show up, and it was 9 out of 36, what do you think the probability of no odd numbers to show up? So they're both even when they show up. If both being odd was 9 out of 36, both being even would be 9 out of 36. Does that make sense? Okay, if you go back through the table there and count like a 2-2, a 2-4, a 4-6, there's going to be 9 of those. Okay, 9 when they're both even. Okay, so now let's use our probability tools that we have, our formulas in the past. If our discrete variable can take on the values of 0 and 2, okay, and we found out that those cumulatively are 18 out of 36, right? So what then is the probability that the dice take on, or my discrete variable takes on the value of 1? So 9 out of 36 plus 9 out of 36 is 18 out of 36, right? That's when we have both even or both odd. And now to have one in the other would be the complement of that, right? So 18 out of 36, does that make sense? Okay. Did somebody say that? I'm sorry, I can't hear you. So we got 18 out of 36. All right, and now you could go through the sample space and count those. But if you're doing that, you're probably still counting where using our formulas for probability, we are already done with that, right? Okay. So now we want to know what our x times p of x is. So remember what we're trying to do here. There should be an x down here in this formula. I'm trying to find the expected value. So multiply these out. You get 0 there, right? I get 1836 there. And I'm going to get 1836 there. The expected value is the sum of your x times p of x's. Well, that's 36 out of 36, right? Which is 1. Okay? So if I do this an infinite number of trials, roll 2 dice, an infinite number of trials, on average, I'm going to get one face to show up even. Does that make sense? That's what that's saying. Now, there will be instances where I get no faces to show up even, right? But there will also be chances where I get both faces to show up even. So those will eventually cancel each other out, correct? In the long run. Okay. So that is our expected value. A couple different ways we write that. Expected value, E of x, or we can write it as mu. Okay. Now what they're asking you to do, and this one isn't too bad to do by hand. They ask you, we're going to find the deviations and we're going to square them and multiply that by the individual probabilities. So x minus mu, so x is my random variable, so 0 minus mu, which was 1. We'll square that and then multiply it by p of x, which is 936. We will then take x minus mu again, so x in this case is 1, minus mu, which was 1, squared, times in 1836. And then we'll go 2, which is this x value, minus mu again, squared, times then 936. The hope is that you see it because we're doing the same calculation repetitively here as we go down these columns. My hope is that you find out that these types of things set themselves up for a spreadsheet very easily, okay, or very nicely. So that's where we'll take this next week, is we'll set up the Excel sheet to calculate these standard deviations for us. When I calculate these, though, what's 0 minus 1 squared? 1 times 936 is 936. Okay. 1 minus 1, 0. 0 squared, 0, right? 0 times 1836, 0. 2 minus 1 is 1. Squared is 1 times 936, 936. Okay, so those are my deviations squared times their individual probabilities. Okay, down here it says we're going to sum those. If I sum those, I get 1836, right? Okay, so 1836, or 1/2. and that is our variance. So how does standard deviation relate to variance? Square root, right? If I take the square root of 1/2, I get 0.7071. Okay? Now, what does that mean to us? Well, if we think about like maybe not knowing what this distribution looks like, does this distribution, is it normal? Is it not normal? If it's not normal, okay, or we are unsure, we could use Chebyshev's theorem, remember that? That said if we go 2 standard deviations above the mean and 2 standard deviations below the mean, then 75% of our data will fall between those 2 values. Okay? If this is normal, let's assume that this is a normal distribution. What that means is that it's the empirical rule then. If I take my mean, which was 1, add to it 1 standard deviation, so it gives me to 1.7-ish, right? Okay? And if I subtract my standard deviation from 1, it gets me to 0.3, correct? So in the ballpark of 0.3 to 1.7, 68% of our rolls are going to show up with face. Now, obviously, it's because they're discrete, you're not going to get like 0.3 faces, right? Okay, but in the long run, we're saying 0.3 to 1.7 faces are going to show up to be even. Okay, 68% of our data will fall on that. Does that make sense? Okay, so again, later on, when we start to see more like appropriate application type problems, so on Tuesday we'll do this question. It says a talk radio station has 4 telephone lines. It says if the host is unable to talk during a commercial or is talking to a person, the other callers are placed on hold. When all lines are in use, others who are trying to call in get a busy signal. So the probability that 0, 1, 2, 3, or 4 people will get through is shown in the distribution. Find the variance and standard deviation of the distribution. What this would do, knowing the standard deviation in the distribution, will tell that company, that radio station, whether based on the amount of callers that they get, whether they need to add a 5th line or 6th line or not. Okay, and there's a lot of things that we have bandwidth issues with our internet all the time here, right? Okay, maybe we could do some statistical analysis to say, maybe we would benefit from having a little bit bigger bandwidth. Okay, so those are things that we can use this probability distribution and the standard deviation to analyze, and we'll talk about that one on Tuesday. If you are looking at that practice test I gave you, question 8 is one of these. Okay, I don't feel comfortable giving you an exam where we've only done one example. Okay, so question 8, it's still going to be on there, but it'll be bonus on Monday's test. Okay, so question about the last question in the last quiz, correct? Okay, so let me pull that up real quick. All right, so it says a bag of 31 tulip bulbs contain 11 red, 11 yellow, and 9 purple. So suppose two tulip bulbs are randomly selected without replacement from bags. So without replacement, so they're staying out. So are these independent or dependent? Dependent, okay. They're asking, let's see here. All right, it says, what is the probability that 2 randomly selected tulip bulbs are both red? So we're going to probability of both red. So what's the probability that the first one was red? 11 and 31. If I pull a red one out, what's the probability that the second one's going to be red? 10 out of 30. Okay, so that's part A. Part B says what is the probability that the first bulb selected is red and the second one is yellow? Okay, so I'm going to write this way. Probability that the second one is yellow given that the first one, first bulb selected is red. Yeah, so like that. Okay, is it okay with everybody? Okay. What is the probability that the first bulb selected is red and the second one is yellow? Actually, that's probably, let's do it this way. First bulb selected is red, so probability of red, okay, times then the probability that the second one was yellow given the first one was red. Does that make sense? Okay, so that's what I should have written. So what's the probability that the first one's red? 11 out of 31, and then 11 out of 30. Okay, this here is just indicating that these were dependent events, right? Telling me that that number there, the sample space is going to change. It's going to be different than the 31 that we saw here. C says, what is the probability that the first bulb selected is yellow and the second is red? Okay? Yeah, it's the same situation. Part D, though, is usually the part that we have questions on, right? It says, what is the probability that one bulb is red and the other is yellow? So here, this idea is the probability that the first one is red, given that the second one is red given the first one was yellow, or the probability that the second one is yellow given the first one was red. Does that make sense to everybody? Okay. It is, but the or, okay, when it says the probability that one bulb is red and the other yellow, there is a probability attached to me picking out the first one being the red one and the second one being the yellow one, and there's a probability with the first one being yellow and the second one being red. So those would be two situations. So with the or here, we actually had to add them. Okay. So when you do this, what's the probability that one bulb is red? So we're thinking about probability that the first one is red. So that would be probability that one is red would be 11 out of 31 times then the second one would have to be yellow, correct? So 10 out of 31. If we go with the probability yellow, okay, then how many of them were yellow? 11 times then 10 out of 30. So these are identical, yes, but we add these results together because a red one then a yellow one is different than a yellow one then a red one. So we have to add those together, and that's why a lot of times if you were to look at your answers, let's see if I can. Now, if you want to go, you can go. I'll keep talking, though. If we look at this, it's going to use different numbers, but we see a lot of times that when you do this, that answer right there that you've typed in is probably half of what the correct answer is. That's because we've got to double that.